Good morning, sir.
Yeah, good morning. So, are there any questions, doubts? Okay, so if there are no questions, doubts, so let me start. So, the last class we were discussing the modeling of 2D truss structures. So, I had taken a structure consisting of two elements, and then we had solved, transformed the element level governing equations, then assembly, imposition of boundary condition, and solution. And then also whatever reaction forces we had got, we verified that they satisfy the overall equilibrium of the whole truss structure. So then next is I am going to now I had said that I will discuss the post processing part. So that is what I will start with, and then of course I'll continue. So 2D truss structure, so that is what, oh, it's not writing. So let me close the file and open it again. Is my screen visible? Hello? Hello, is my screen visible?
Yes, sir. Yes, sir.
Okay. So we were discussing now this 2D truss structures. So although I took a simple example, but no, any number of members can be there. It would be modeled in a similar manner. Of course, it may not be possible to solve the problem manually. Maybe either you will have to develop your own code, say in MATLAB, Python, Fortran, C, whatever, or you use a commercial FE software to do this. So only thing is, no, you have to create each member of the truss structure would be modeled as a line, and then each member you have to mesh using one two noded truss element, and then of course apply the boundary condition and loading and solve the problem. Then you will get the displacements, reaction forces, and also through the post processing stresses in the different members. So that is what one can do from this. So now the example I took was this one. So that is so each member here, no, they are connected through a pin joint. So there's no rigid connection here. This is a pin joint, and we had said the forces are P1 and P2. The nodes we had numbered as global node numbers 1, 2, 3. The elements are, this is 1, this is 2, and the global coordinate axis is very small x and y. And for this element this was capital X, and for this element this was capital X, and we said this angle is 45, and similarly this angle is 45, and the length of each member was L. Cross sectional area was EA, no, area and Young's modulus product is EA, so this was EA. So this is the displacements we have solved. So if you remember, of course, we have solved for u1 v1, u2 v2, and u3 v3. So u1 v1 are 0, u3 v3 are 0, u2 v2 we have solved. So now we want to do post processing. So post processing means the calculation of displacement at anywhere within the element, and also the basically strain and stresses within the element. So now if we take element 1, so element 1 is, this is the element number 1. So for this element, if you look at the u1, is 0. We have the element 1 is consisting of global node numbers 1 and 2. So the displacements we have already got u1 equal to 0, v1 equal to 0. So this u1 v1 are the displacement along small x and y direction, that is global coordinate directions. And u2 we have solved, and we got it as p1l upon a, and v2 also we have solved and got it as p2l upon a. So this is what we have got. So now, before you can do the post processing, because within the element, if you look at the interpolation is of the displacement in the local x coordinate, no, this capital X. So we will have to first get the uh, elemental degrees of freedom in local coordinate system, that is in the displacement along the capital X direction within the first element. So we use the same transformation relation. So let us say u for subscript is node number, local node number, and superscript is element number. So u11 and u21 would be equal to, as this T transformation matrix. So you can recall, no, that we had written that this DE is equal to basically T into capital D. So we are kind of making use of this. So this is transformation matrix, and for the first element we have seen it was 1 upon root 2, 1 upon root 2, 0 0 0 0 1 upon root 2, 1 upon root 2, that is cos alpha and sin alpha we had said. And this side we will have u1 v1 u2 and v2. So now as you see u1 v1 they are already 0. So you will get the first, when you multiply this first row with this column, you will get, because this u1 is 0, v1 is 0. So the first will be 0, and the second term would be of course u2 plus v2 by root 2. u2 plus v2 by root 2. So that is what you will get when you multiply this matrix with this vector. And now if you substitute the values of the u2 and v2, so this will remain 0, and this will become p1 plus p2 into L upon root 2 into ea. So the that means the displacement along length of the element is, first node it is 0 because no, it is pinned here, so that cannot move. But the node 2 along the length of the element, the displacement is p1 plus p2 into small l upon root 2 into ea. So this is the displacement. Now once we know the vector of elemental degrees of freedom in local coordinate system, so then we can write u. So u will be equal to the shape functions. So 1 minus x by l and x by l, these are the shape functions for a two noded truss element, and into the vector of elemental degrees of freedom. So u11 u21. So now if you put the values, u11 is already 0 as we have got over here. Basically you can say 1 minus x by l, and u11 is 0 and u2 is p1 plus p2 into l upon root 2 into ea. So then no, you can, so if you multiply, so this will be simply p1 plus p2 into x, because no, this L and this L will cancel and x will come over there, and divided by root 2 into ea. So this is what you get as the displacement. So if you want to calculate the displacement at any point along the length of the element, so you put the value of no, this is small x, x equal to small x equal to 0 is the first node, x small x equal to L is the second node, and if you put any value, let's say x is equal to small l by 2, you will get the displacement at the center of the element along the local element x axis. And then the strain epsilon xx will be du by dx, and which would be p1 plus p2, because you are differentiating it with respect to capital X, that will go. So p1 plus p2 upon root 2 into ea. So this is what you will get as the strain, and this strain is a normal strain along length of the element, so that you have to keep in mind. So it is not in the in terms of global coordinate system, but in terms of local coordinate system. So sigma xx would be E times epsilon xx, so that would become P1 plus P2 upon root 2 into A. So this is the stress in the first element. So which is P1 plus P2 upon root 2 A is the stress. So this is the member, the first the first element we are talking about. So if you take any cut section over here, if you take any cut section, so the stress here is, this is what sigma xx, and this side also if you cut it, so obviously that side also is sigma xx. So this is P1 plus P2 upon root 2a. So this is the stress. You'll have to make sure that this stress is less than the design stress, no allowable stress in the material of the truss member. Now, then going to the element 2. So for element 2, it is as you see over here, element 2 is consisting of global node number 2 and global node number 3. So it is defined between global nodes 2 and 3, and we have already said that U2 is P1 into L upon EA, and V2 is P2 into L upon EA, and basically U3 is equal to 0 and V3 equal to 0. So this no, we have already got. And so now we want to use the same relationship, that is D equal to T into this capital D. So we are using this transformation relationship. So we can write now the displacement, the local node along the capital X direction and local node 2 along the capital X direction. For the element number 2 will be the transformation matrix, and for the second element we had said alpha is minus 45 degrees. So transformation matrix is 1 upon root 2 minus 1 upon root 2, because cos alpha sin alpha. So cos alpha is 1 upon root 2 minus 1 upon root 2, 0 0 0 0 1 upon root 2 minus 1 upon root 2, and into then the displacements, which are basically u2, v2, u3 and v3 for the second element, because it is consisting of global nodes 2 and 3. So if you again do this, so you will see that this multiplication u3 and v3, they are already 0. So you will essentially get this as u2 minus v2 upon root 2. That's the first term, and second will be actually equal to 0. So you can ultimately say that u12 small u. So keep in mind that is difference between no, small u and capital U. I'm the kind of notation I'm using. So this is small u12 and u22 will be equal to, if you put the values of u2 and v2, it would become basically P1 minus P2 into L upon root 2 into EA and 0. So yeah, these are the values of the displacement along the local x-axis for the second element. And for the second element, we are already saying no, this is the local x-axis. So the displacement, this is u12, and for this node this is u22. So this is actually coming out to be 0, and this is what we have got, P1 minus P2 upon root into L upon root 2 into EA. Yeah, so once we have got this, then we are interested in finding out the displacement along the length of the element at any location x. So we make use of the interpolation. So 1 minus x by L, and then we have this u12 and u22. And if you put the values, so now we know that u22 is already 0, u12 is given by this. So if you multiply, so this will come out as basically uh, you will have first term will be P1 minus P2 and into L divided by root 2 into EA. So this is the displacement P1 minus P2 into L upon root 2 into EA. into the shape function, which would be 1 minus x by L. And second term is basically, yeah, that's only single number. So after you multiply, so that's just a single number. So this is what you get as the displacement. So using this relationship, you can calculate the displacement at anywhere within the element. And then the epsilon xx would be equal to du by dx. Now we are doing the calculation for the second element. So if you differentiate, so these are all constant terms. This is also constant. So you will get minus 1 by L. So minus, if you multiply, you can write that as P2 minus P1, and then actually L will go and you will have root 2 into EA. So this is what you will get, and then sigma xx, the stress will be E times epsilon xx, and that would be P2 minus P1 upon root 2 into A. So this is the stress in the uh, the second element, and it is of course constant throughout the length of the element. So throughout the second member of the truss, the stress is constant. Now I wanted to show you the cross check. If we wanted to directly check whether this result, let's say, we want to look at the stress. So the first element we got, know the stress along the length of the element, normal stress along length of the element, P1 plus P2 upon root 2A, and stress in the second element along the length of the element is P2 minus P1 upon root 2 into A. So what you can do is actually, you can use a method of joints and find out the forces in the members. So maybe in the first, the basic mechanics, engineering mechanics course, you might have done this. So just a check, we want to do a check. So for the check, I am going to use method of joints. So method of joints means, let me draw the free body diagram of joint 2. So FBD, F means free body diagram, FBD of joint 2. So what we do now, if you look at the joint 2, there is an external force. So there is a P1 there is a P2 there. The force where the point where the forces are applied, and then also these two members, 1 and 2, element number 1 and 2, are also going to exert force. So usually in the in this we denote this force by member 1 as F1, and force exerted onto the joint by element 2 as F2, and this angle is 45 degree, and this is also 45 degree. So what are F1 and F2? So we are assuming in the method of joints that first member is subjected to force so this is force, and no, similarly the second member is subjected to force F2. So this is a method of joints, and the coordinate system is say this x and y. So if we write sum of forces along x direction equal to 0, because the whole truss structure is in equilibrium, so each joint also has to be in equilibrium. So sigma fx equal to 0 will give you along x direction, and the force is P1. So this is force P1, and then F2 will have a component, say F2 cos 45, and cos 45 is 1 upon root 2, so F2 upon root 2. And then the component of F1 in this direction will be minus F1 cos 45, which would be minus F1 upon root 2 is equal to 0. So this equation can be written as, say, F1 minus F2 is equal to root 2 into T1. So this is one equation, and let me call today as this as equation number 1. And then similarly, if you write sum of forces along y direction equal to 0, the y direction forces are, this P2 is there. So we are writing this equilibrium equation for joint, not P2. So this is P2, and then both F1 and F2 will have component along the negative y direction, F1 sine 45 and F2 sine 45. So that is 1 upon root 2. So we will get minus F1 upon root 2 minus F2 upon root 2. This will be equal to 0. So you can write from this equation that f1 plus f2 is equal to root 2 into p2, and let us call this as equation number 2. So now if you solve solution of equation 1, equations 1 and 2 will give you, so it is straightforward. If you add, you get f1, so you will find that f1 will come out as p1 plus p2 upon root 2, and you will see that f2 will be p2 minus p1 upon root 2. So f2 is p2 minus p1 upon root 2. So now these are the forces. Now to calculate the stress, you have to simply divide by the cross sectional area. So the cross sectional area is A. So stress in the first truss is going to be P1 plus P2 upon root 2A, and stress in the second member is going to be P2 minus P1 upon root 2 into A, which is exactly same as what we have got over here. So in the first element we have got this as the stress P1 plus P2 upon root 2 into A, and from in the second element we have got P2 minus P1 upon root 2 into A. So now you see that for this case we get the finite element is giving us the exact solution what we get from the method of joints, because the forces are acting only at the nodes, so there are no distributed forces. So in that case the displacement within each element will be linear in capital X, and that is what we have already assumed in the approximate solution in FE. So FE gives you the exact result no, for this particular case. So no, this, although I know if the this was a statically determinate truss structure, so we are able to use method of joints and find out F1 and F2. But if it is indeterminate, the FEM would be applied exactly in the same way, and then you can get the force, the stresses in each member, and then look at whether it is safe or unsafe, or you want to change the cross sectional area so that the stresses in all the members are within the allowable stress. So you can do those calculations easily using finite element. So with this example, let me move on. So the next is I wanted to discuss about modeling of 3D truss structures. So now in the 2D truss structure, I had said that all the members are in a one plane. Now 3D truss structures would be where the members, the truss and the members of a truss structure would be oriented in a three-dimensional space, and of course all of them would be in that case would be connected through the ball and socket joints. So the for the 3D truss structures, the joints would be ball and socket joints, and in the 2D truss structure, I had already said that the at joints the members are basically concurrent. So although they may be connected through the welding or through a gusset plate, so at the joint a plate is there in which all the members are welded. That is known as the gusset plate. But the members would be concurrent, and if it is so, we treat that as a the truss structure. In the 3D truss structures, the joints are going to be ball and socket joints. So that is modeling of 3D truss structures. So the members are oriented anywhere in space. So I'm not going to go into too much details. The method would be extended exactly in a similar manner the way we did for the 2D truss structures. So I'll just let me talk of the straight away the transformation. So let us say that this is the element, this is the local node 1 of the element, and this is the local node 2 of the element. The local coordinate axis is along the length of the element, so that is capital X, but the global coordinate axes are, let us say, small x, y, and z. So these are the global coordinate axes. The displacement along the global coordinate axes are u1 for the first element u1e, along this is v1e, and along z it is w1e, and similarly at the second node we will have u2e, along y direction v2e, and along z direction w2 into e. And in terms of the local coordinate axis, the displacements are u1e, and at this node the displacement is, at this node the displacement is u2e. And let's say length of the element is small l, Now, to write the transformation matrix, we need to express this u1e and this u2e in terms of displacements capital U1, capital V1, capital W1, capital E2, capital V2, and capital W2. So for that, we need what is the orientation of the element, that is the orientation of the local x-axis with respect to global x, y, and z coordinate directions. So let us say that alpha is the, you need to get these coordinates so from the data. So when you create the structure, so let's say alpha is the angle between capital X and small x. Beta is, let us say, angle between capital X and small y. And gamma is, let me use gamma. So gamma is the angle between capital X and z. So if these are the angles, so you can write the direction cosines. So cos alpha and cos alpha can also be written as, if you know the global coordinates of node 1 and 2, global x and x, y, and z coordinates of nodes 1 and 2, and then of course if you know the coordinates, you can always calculate the length. So the direction cosine cos alpha would be x2 minus x1 upon L, and cos beta would be equal to y2 minus y1 upon L, and cos gamma would be equal to z2 minus z1 upon L. And you know that then L element length will be, it can also be written as x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. So once now you have these direction cosines, then now you want to write this displacement along the capital X direction, that is u1e. So you will have to take the component of this capital u1e along capital X direction. You have to take the component of this capital V1e along the capital X direction, and you have to take the component of this W1e along the capital X direction. So if you write that, you will actually say straightforward that no, you can write this small u1e would be equal to no, this capital u1e cos alpha plus capital v1e cos beta plus capital w1e cos of gamma. And so similarly you would be able to write at the second node, that is u2e would be equal to u2e cos alpha plus v2e cos beta plus w2e cos gamma. So now if you want to write this in the matrix form, so you can put both these together. So you can write u1e and u2e. I'm just trying to write the transformation matrices we have done earlier. So for the 2D truss structure, now same thing we are extending it for the 3D truss structure. So we are basically the assumptions within each element are the same. That is, no, the displacement, only non-zero component of displacement along the length of the element is that is small u, it's a function of x. Only non-zero component of stress is sigma xx along length of the element, normal stress along the length of the element. All the stresses are actually zero, all other stresses, and the stress sigma xx is uniform throughout the cross section. So those assumptions are there. Now, when we say 3D truss structure, means it is not a 3D element. It's only that the member is oriented in a three-dimensional space. So U1E and U2E would be then cos alpha, cos beta, cos gamma 0, 0, 0, and 0, 0, 0, cos alpha, cos beta, cos gamma, and then the vector of elemental degrees of freedom in global coordinate system. So U1E, V1E, U2, yeah, and yeah, W will be also there. So W1E and U2E, V2E, and W2E. So you can write now this relationship. And in the notation form, we say that this is D, the vector of elemental degrees of freedom in local coordinate system, which is 2 by 1 vector. And this is the transformation matrix, which is 2 by 6 vector. And then this DE is the vector of elemental degrees of freedom in global coordinate system, This is a 6 by 1 vector. So the names of all these variables are exactly the same. So this is D and that is T. So this is the vector of elemental degrees of freedom in the local coordinate system, and this is a vector of elemental degrees of freedom in the global coordinate system. Now we have already discussed how to derive the finally element level governing equations. So you know the element level. Now the transformed I am talking about, after the transformation we now write this small d in terms of a capital D, and also pre-multiply the element level governing equation by T transpose, so we get the transformed governing equation. So element level transform governing equation will be basically same notation I am using, Ke bar into De is equal to, and we are assuming that there are no distributed forces in the element, so we have only this internal force F internal E. So now here where if you see we have already derived earlier for the 2D truss structure, so only thing is the transformation matrix is different, otherwise everything is same. So here the Ke bar is nothing but T transpose into Ke into T, and basically this T matrix, and the F internal E transformed is equal to T transpose into F internal for the element. So you know where basically you have this Ke, you know, is the same stiffness matrix for a two noded truss element, which is Ea by L, 1 minus 1 minus 1 and 1, and F internal, you know, it is equal to minus Q1E and Q2E. So yeah, this is how we will have the governing equation for a 3D truss element in the common coordinate system, okay, small x, y, and z. So before assembly, you have to transform the stiffness matrix of each element using this relationship. You have to transform the internal load vector using this, and actually you will find that T transpose into F internal gives you the force along the global small x, y, and z direction. So you can directly write at each node what are the forces either known or unknown along global x, y, and z direction on the right hand side after assembly. So, and then you can solve the problem. So I am not going to take an example on this, but you should be able to solve any 3D truss structure problem using this transformation and the equations and solution and so on. So the solution procedure would be exactly same what we discussed for the 2D truss structures. So now, yeah, I think uh, I skipped the heat transfer problem. I actually wanted to discuss a heat transfer problem in a cylindrical body with temperature gradient only along the radial direction, but I think I'm skipping that, and then moving on to now. So far in the as far as the finite element is concerned, I have discussed this element. Truss element means the displacement is along, the forces are along the length of the element, and the stresses and strains are also normal stress and strain, non-zero stress and strain are along the length of the element. Now the other situation you deal with is, for example, if you either look at the ship or submarine, I think I will be most of the time taking these as examples. If you look at the, I don't know, you would have seen the stiffeners. So you have stiffeners running along the length. They are typically called stringers, and you have the stiffeners running along the circumference, which are known as rings. So you have these stiffeners, and let's say there is a hydrostatic pressure from the outside, so which would be acting, no, ultimately would be transferred to the these stiffener, no, the stiffeners and rings as a transverse load. So if we want to model those rings and stiffeners, we will have to use what we call as, the beam elements. So the first simplest element in beam is what is known as the Euler-Bernoulli beam element. So the next I am going to discuss basically Euler-Bernoulli beam element. So before I go to Euler-Bernoulli beam element, I just want to give you a brief introduction to what are the different concepts involved in Euler-Bernoulli beam element, which is a summary of what you would have learned in your strength of materials, the basic course on strength of material or solid mechanics. So Euler-Bernoulli beam. This is also known as classical beam. So in this first time, this is not the finite element, but first some concepts of no Euler-Bernoulli beam I am discussing, so that no you know all the things which are involved in this. So let us say this is the beam, and the coordinates are no this is small x and this is small y, and the length of the beam is L. I am just taking a very simple case, and height of the beam is say h. So the very basic assumption is that in the Euler-Bernoulli beam theory, the very basic assumption is that beam is thin. So very basic assumption is beam is thin. So how do we say thin? So if this height to length ratio, if this is less than much less than 1, then we say the beam is thin. And typically h by L could be less than 0.05 for homogeneous isotropic beams. Homogeneous isotropic beams. And we are talking about the statics problems. In the dynamics problem, if you want to say whether it is check whether it is thin or not, then you have to, in a dynamics problem there would be vibration modes, and each mode would have some wavelength. So you have to then check wavelength to h2 wavelength ratio h by lambda, and if h by lambda is less than 0.05, you can still say that for that mode the beam can be treated as a thin beam. So now once so the what are the implications of this thin beam? That normal to the beam remains normal after deformation and straight. So if I take this is the center line, and if I take the normal, so this is the normal. This is at 90 degree to the the central line, and after the deformation this normal remains straight and normal to the central middle surface or the neutral surface, and and these are the consequences of this assumption that beam is actually thin. So now we talk of deformation. So if we talk of deformation of the beam, so the deformation means this is the beam in the undeformed configuration, and these are the coordinates x and y, and let us say now this beam deforms like this. So this is the deformed center line. The deformed center line would be like this. Now if I take any normal here, normal to the center line, so this is the normal, this is the normal, and if I extend it, it goes there, and then this normal will go to somewhere, it will become like this. So and I think still it is not at 90 degrees, so let me draw it again. So this normal, no, the initially this is the normal, it goes over there, and this angle, no, if I draw a tangent, this angle still remains 90 degrees. And if you look at the slopes, so if I draw a tangent here, so with respect to the original central line, this angle is basically dv by dx. So similarly, this angle between the initial orientation of the normal and the deformed normal, it is dv by dx. And if I take any point over here, say this point, so this distance, this particular distance is going to be y into dv by dx. So this is undeformed configuration. This is undeformed, and this is the deformed configuration. And now if you now if you remember when I was talking about the big form and the integral functional, so some of the things I have already discussed, so I'm just kind of repeating that. So now if you talk of displacements, so you have displacement along x direction, which is a function of x and y, so that is equal to minus y into dv by dx. Basically this displacement which I have marked there. So since the point is moving, initially this point was somewhere here, and finally it has gone here. So this has moved along the negative x direction, and the distance is minus y into dv by dx. That is y is the height, and in dv by dx is angle. For a small deformation we are just writing it as basically the uh, radius into a kind of no angle. So r equal s equal to r into theta kind of the expression. And this is be called as the axial displacement, because this is axial means along the axis, axial displacement. And then v, you have transverse displacement, which is known as the function of x only, transverse displacement. So these are the displacements. And then if you look at the strains, so only one independent component of strain is, right now we are talking in terms of a global coordinate system, so let me use small xx. So epsilon xx is going to be basically del u by del x, and this u is in terms of this expression, so we will have minus y into d2v by dx square, because we are differentiating once again with respect to x, so we will have second derivative of this v. So that is the strain. And then if you look at the stress, so you will have sigma xx, which is E times epsilon xx, again the uniaxial state of stress. That is sigma xx is non-zero, sigma yy, sigma zz, tau xy, tau yz, and tau zx. All the other stress components are zero, so we will have this as minus ey into d2v by dx square. So this is the stress, and as I already said, sigma yy is approximately zero. Why I am saying approximately zero? Because if the beam may be subjected to a distributed force, let us say at the top surface there is a distributed force, and under the action of this force the beam deforms like this. So and then the top surface, basically there would be non-zero sigma yy, which would be equal to this applied force divided by the width of the beam, but that would be much smaller compared to the maximum value of sigma xx. So why I'm saying that this is approximately zero? Because sigma yy maximum value of sigma yy is much less than the maximum value of sigma xx. So that is why we have this assumption in the beam. And similarly sigma zz is also actually equal to 0, and tau xy equal to tau yz equal to tau zx. In the Euler-Bernoulli beam theory, all these stresses are 0. If you look at the strain, so from the Poisson's effect, you will have epsilon yy equal to minus nu times epsilon xx, and similarly epsilon zz would be equal to minus nu times epsilon xx. So this is a complete picture of the stresses and strains in the element. And of course the other shear strains would be 0, so gamma xy equal to gamma yz equal to gamma zx. So these shear strains are going to be actually 0. So yeah, so why I am telling you all this, because you should know what are the assumptions. So when you are choosing a particular finite element for solving a problem, so you should know what are the assumptions made, and whether those assumptions are valid for a given problem or not. So that you have to always check. So now let me also earlier when I had discussed the big form and the integral functional, so I had taken that fourth order differential equation directly. So let me derive that, and so how to get the differential equation for beam, and then of course the big form and integral functional we had already done, so I will not be repeating that. So before I go further, let me define the bending moment. So bending moment, and bending moment I am going to denote for the timing actually the moment about z axis. So this is about z axis. So in the beam, we have already taken this coordinate system. This is x, this is y, then z would be like this. So bending moment is actually the moment about z axis. So now if you look at any cross section of the beam, so let me say, take a cross section of the beam. So this is the cross section of the beam. Let us say the coordinate normal to this cross section is x, and along the height we have y coordinate, and we have this z coordinate in the third direction. So basically x is normal to this cross section. This is the beam cross section. Beam cross section, x is normal to beam cross section. So now if you look at any small area dA, so let us say this area dA. So in this area, as we know, there is a stress sigma xx is there, the stress, and this area, the centroid of this small area is, let us say, at a distance y. Then the bending moment is what? Mz is the bending moment. So if you look at the force, that is sigma xx into dA is going to be the force, and then moment is going to be this is the force multiplied by y gives you the moment, and but this will give you the moment about no negative z axis, but we are talking about a positive bending moment, which is on a section whose outward normal is along positive x direction. The bending moment would be positive about positive z axis. That's the sign convention. So we will put a minus sign and then integrate it over the entire cross sectional area to get the bending moment. So therefore mz is equal to minus y sigma xx into dA. So this is the bending moment expression. And now you write, no, you put the value of sigma xx, we have already said. So minus integral y is there, and sigma xx we have written minus e into y into d2v by dx square dA. So you will see here, I know that d2v by dx square is only function of x. The integration is only with respect to cross section, and this minus minus will also cancel. So we will have e y square dA, and into d2v by dx square can be taken out of the integration sign. And this we know y square dA is the second moment of area about the z axis. So we can write that as e into izz into d2v by dx square. So where basically izz is your integral y square dA. You call it as second moment of area. So you would have done the bending stresses in beams, and there you will have used this second moment of area or area moment of inertia. So integral y square dA. So yeah, this is the expression for bending moment. Mz equal to E into Izz into d2v by dx square. So this is the bending moment. Now let's also, as I said, after this, let us derive the governing differential equation. So when we want to derive the governing differential equation, so we need to consider the free body diagram of a small element of the beam. So no, that means if this beam is there, we take a small element, take a cut section here, and say of length delta x, and draw the free body diagram of this portion. So we consider a small element, and when we draw the free body diagram of that small element, so there is a distributed force, that is, let us say q is there, and let us say this side we have point A, and on the right hand side there is going to be shear force. Shear force I am denoting by sy. So s subscript y, and in there we know when we go from left to right there is going to be some increase, so I am saying that as delta sy. Similarly, there is going to be bending moment. The coordinate directions are same. this is x, this is y, and this is z coming out of the screen. So at this side, no, the right hand side outward normal to the section is along plus x direction. So the shear force is positive along positive y direction, and the bending moment is positive about positive z axis. So this is the bending moment, which is mz plus delta mz. And the left hand side, because outward normal is along negative x direction, so the positive shear force would be along the positive along the negative y direction. So this is the positive shear force, and the bending moment would be about negative z axis. So this is the bending moment here. So on the left we are taking shear force as sy, bending moment as mz, and they will change in general as a function of x. So the right side there is a shear force sy plus delta sy, and the bending moment is mz plus delta mz. So these are all the forces acting on the small element. So here we have already said mz is, the already we have defined it to be bending moment, and sy we have said as shear force. So now the equilibrium equation. So how do we write the equilibrium equations? So one equilibrium now, because in the sigma, if you write the sum of forces along x direction equal 0, that is trivially satisfied, because as of now there are no forces along the x direction. So main equation we get, one is from sigma fy equal to 0, sum of all the forces along y direction equal to 0. So basically this will give you sy plus delta sy is the force along plus y direction. This is the force along negative y direction, so minus sy. And then we have this q, which is force per unit length. So will have q into delta x, and actually no, q could in general be function of x. So we really need to take the average value of q over that length, and then into delta x is equal to 0. So you will see that this delta sy, and plus we will have q average into delta x equal to 0. Then what you do, you divide it by delta x and take the limit. So we will have delta sy upon delta x plus q average equal to 0, and then take the limit, delta x going to 0. The first term will give you dsy by dx, and then the q average will become the exact value of q at a particular point x. So this will be one equation. So let me call this equation as, so let me number the equation. So I think the bending moment equation, let me number. So we have already used, I think, the equation numbers 1 and 2. So let me number bending moment equation as equation number 3. So let us say this is equation 3, and this is, let us say, equation 4. So this is one equation, and then second equation we get some of the moments about z axis passing through point A equal to 0, taking, say, the moment about positive z axis as positive. So this will give you, now as I said, no, in the free body diagram we are considering this free body diagram. This is already the moment about positive z axis, this is the moment about negative z axis. So we will have mz plus delta mz minus mz. So this, and then you will have, of course, we are taking moment about A. So this sy is passing from the same point, will not produce any moment, but this shear force sy plus delta sy will produce a moment, and this force due to q will also produce a moment. So you will have mz plus delta mz minus mz, and plus you will have this sy plus delta sy into delta x you will have, and then plus kind of I'm taking q average into delta x as the force, and you can assume that it is at a distance delta x by 2, this is equal to 0. This last expression actually is an assumption that q is constant throughout that element equal to q average, and then in another moment can be written like this. So this is what you get. And in a similar logic, then divide the whole thing by delta x, and then take the limit delta x going to 0. So you will get dmz by dx plus sy equal to 0. So this will be the equation number say 5. From this equation you can also say that sy shear force would be minus dmz by dx. And now mz we have already written, so we can say this would be d by dx of mz is eizz into d2v by dx square. So yeah, this is another equation. So let me say equation number 6. So you now know the bending moment in terms of displacement v, transverse displacement, is ei into d2v by dx square, and the shear force sy is minus d by dx of eiz into d2v by dx square. So this is the shear force. And now what we can do is once we have know this expression of sy, and we can substitute know the 6 in equation number 4, and get the final governing differential equation for the beam. So now you can say that substituting equation 6 in equation 4, we will get, so first term is dsy by dx. Asy is already this, so we will differentiate it once more. So we will get d2 by dx square, and then eizz d2v by dx square plus q is equal to 0. So this is the governing differential equation for the beam. And you remember we have used this equation. Now we have earlier used this equation no to solve the either no we have used better residual method or big form integral functional. So we have used this equation. So this is the same governing differential equation for Euler-Bernoulli beam. So today I have shown you how to derive this. So for this differential equation we have already discussed WRS, weighted residual statement we have discussed. We have already discussed big form, so how to get the big form for this, and we have also discussed how to derive the integral functional. So we have already discussed these concepts, are already discussed for this problem. So I'm not repeating that again. No, you can go through. So now once with this background theory of Euler-Bernoulli beam, let us move on to the Euler-Bernoulli beam finite element. So now I'm going to move on to Euler-Bernoulli beam. And of course no if you recall you would have done of course the deflection of beams, and in the deflection of beam you might have actually used equation number 3, no, so writing down the expression for bending moment in terms of applied forces, and then integrating this twice, finding out the constants of integration through the boundary condition, and then finding out the deflection and all you would have done. So actually you would have used this equation. Maybe I don't know, some of you also might have used this fourth order differential equation also. This can also be used for finding out the deflection, but we want to we are not right now looking at the exact solution of this differential equation, but finite element solution. So now Euler-Bernoulli beam finite element. So this is what we are going to discuss. So now beam a finite element, as we say, the differential equation is fourth order. The integral functional, we see the highest derivative is in the integral functional is going to be d2v by dx square. So the second derivative, and the primary variables we have seen are v and dv by dx. So then v and dv by dx, which are the primary variables, have to be degrees of freedom at the the end node of the element. So we consider a two noded element, Euler-Bernoulli beam finite element. So this would be the local coordinate capital X, and this is the y coordinate. The degrees of freedom are going to be the displacement, transverse displacement, so along the y direction. So let us say that is v1 at first node, and the derivative of v, that is basically dv by dx at node 1, and let us denote this by theta 1. So theta 1 is the dv by dx at node 1. So this is for the element. So ith element is, let us say this is E. So I'm putting superscript E denoting the element. And similarly at the second node, the degrees of freedom are V2E, and we have rotation, that is dv by d capital X. Now because we are using this, no, the local coordinate capital X, so the derivatives are with respect to at node 2 for the element, and let us denote it by theta 2e. So these are the 4 degrees of freedom of the element. This is local node number 1, local node number 2, and let us say length of the element is small l. So this is the element degrees of freedom. So degrees of freedom are V1, V1e, theta 1e, V2e, theta 2e. So there are 4 degrees of freedom for the element. So elemental degrees of freedom are now 2. Elemental degrees of freedom are 4, and the nodal degrees of freedom are 2. So earlier, no, for the truss element we had only single nodal degree of freedom, but now we have 2 nodal degrees of freedom. And in the same element, if we want to show the forces, so if you also want to show the forces in this finite element, so this is node 1 and this is node 2. So because there would be no, the elements on the left and right, so there would be shear force exerted by element on the right side. So let us say that is sy2 for the element, and there is a bending moment. Now let us say mz2 for the element, and similarly the left side you will have sy1 for the element, and you will have bending moment which is mz1 for the element, and there is a distributed force. So these are the I think the arrow is not very well done. So this is mze. So these are the and there can be distributed forces q, and no, this is for the entire element. And of course within the element you can always take a small differential length delta x, and this is x coordinate. So no, this is the element we are talking about. Now let us use simpler notation for area moment of inertia. So let me denote iz by I, and let me denote bending moment mz simply by m, and the shear force sy simply by s, and dv by dx of course we are already denoting by theta. So let us use these notations, and in light of these notations now you can see the total integral functional or total potential energy functional. Total potential energy functional is be denoted by I, so half of strain energy. So integral 0 to L, we have derived this. So I am using the same thing, EI d2v by dx square whole square dx. Yeah, the derivatives are with respect to know the global x. So let me put that. No, the local x. So this is dx2 dx, and then minus integral 0 to L this potential of distributed force small q, so vq dx, and then you will have potential of these forces. So this sy1 does a negative work because v1 is the along the positive and this is along the negative y direction, so potential would be positive. So we have already discussed, plus you will have s1e into v1e, plus you will have m1e into theta 1e, and minus s2e into v2e, minus m2e into theta 2e. So this is the total potential energy functional. We have already written it earlier, only now we have written it for one particular element. So once we have this integral functional, so then we talk of the approximate solution. Yes, somebody asked a question in between. P1 and P2 are external forces. Yes. So Sirijit, yes, P1 and P2 are external forces. I had in the last class itself we have talked about those. So P1, P2 are external forces, and then we have calculated the stresses. So sorry, I didn't see this chat. So no, yeah, these P1, P2 are external forces. Yes, in the truss problem. Are there any other questions? Are you listening to me? Hello, am I audible? Okay. So then, now we have to develop the element level governing equation the way we did for the truss element. So the next step is to assume an approximate solution. And this Euler-Bernoulli beam theory is also referred to as classical beam theory. So sometimes, rather than Euler-Bernoulli, we just say classical beam theory. So that you should keep in mind. So then the approximate solution is, we look at, no, there are three things we had discussed: differentiability requirement, inter-element continuity requirement, and the completeness requirement. So these are the three, and of course for the 2D and 3D you have additionally geometric invariance. So, as per the differentiability requirement, highest order derivative, second derivative. So, whatever we assume as V, that should be at least a quadratic polynomial. And from the completeness requirement, then we should have a constant term and a linear term. So, we will have then A0 plus A1x plus A2x square. But if we just have these three terms, so then we have only three constants A0, A1, and A2. But there are four elemental degrees of freedom: V1 theta 1 and V2 theta 2. So we should have at least four unknown. And why we have V1 theta 1 and V2 theta 2 as degrees of freedom? Because we want to have primary variables V and dV by dx, which is denoted as theta, as degrees of freedom at the end node. So both side two nodes becomes 4 degrees of freedom. So then we have to have basically four terms in the approximate solution. So the minimum solution, approximate solution, we can assume for this Euler-Bernoulli beam finite element is a cubic polynomial in X. So this is the minimum requirement, the first three terms. Minimum requirement based on differentiability, minimum based on differentiability requirement. And then the last term, this is additional term added to have degrees of freedom each node to satisfy the inter-element compatibility, or the inter-element continuity. So this is added to have 2 degrees of freedom DOFs at each node. And these two DOFs are what? The primary variables. So basically 2DF means primary variables. So this is to satisfy the inter-element compatibility. This is to satisfy inter-element compatibility. That is continuity of primary variables across the elements. So this is, once we have assumed this approximate solution, so in the finite element, the next step is to express these constants A0, A1, A2, A3 in terms of values of the displacement, and in this case derivative of the displacement at the node points. So as you know, at capital X equal to 0, left end of the element, we have V equal to V1E. And so this will give you, so if we put this is equal to V1E and capital X equal to 0 on the right hand side, so we will get simply A naught is equal to V1E. And no so you can number this equation. So yeah, so last number we have is 6. So let us call this as 7, this equation as 8. So let us say this equation is 9. And then at x equal to 0, we also have dv by dx is equal to theta 1 e, and that will give you basically what you need to do is you have to differentiate this expression with respect to x and then put x equal to 0. So you will get basically a1 equal to theta 1 e, and let us say this is equation number 10. Then at the second node, right end x is equal to small l, you will have again v equal to v2e, and this will give you an equation v2e equal to a naught is already v1e and a1 is already theta 1e, x is l, so we will have l plus a2l square plus a3l cube. So this is, let's say, equation number 11. And then also we have at x is equal to l, dv by dx is equal to theta 2e. So this will give you, no, this equation will give you another equation theta 2e equal to theta. No, you have to differentiate and then put, of course, a1 is already theta 1e, so you put that, and this will be 2a2 into l. You're differentiating and then putting x is equal to l. So you have 3a3l square, and this is, let us say, equation number 12. So we already, from the equation 9 and 10, we already have a naught and a1. A naught is v1e and a1 is theta 1e, and we can solve equation 11 and 12 for a2 and a3. And if you solve, so I will leave the solution for you to check. So solution of equations 11 and 12 will give you a2 is equal to minus 3v1e by l square minus 2 theta 1e by l plus 2v2 e by l square and minus theta 2e by l. So if you solve equation 11 and 12 for a2, you will get this as the solution, and if you solve it for a3, so similarly, the solution for a3 will come out as, you should cross check this, solve equation 11 and 12 for a2 and a3 and check that whatever I have written is correct or not. So this will come out as this, theta 1e by l square minus 2v2e by l cube plus theta 2e by l square. So these are the solutions. Now what we do, once we have got a0, a1, a2, a3 in terms of v1e, theta 1e, v2e, theta 2e, so we put all these values a0, a1, a2, a3 in this. So here you put values of a0, a1, a2, a3, and then collect the coefficients of v1e, theta 1e, v2e, theta 2e, and those coefficients are known as shape functions. So then ultimately you would be able to write finally v equal to, in terms of shape functions, and now these shape functions are known as Hermite shape functions, so I am denoting them by h. So you will have four shape functions because there are four elemental degrees of freedom, into, you will have v1e, theta 1e, v2e, and theta 2e. So where now these h1, h2, h3 are Hermite interpolation or shape functions. So these are Hermite, they are known as Hermite interpolation or shape functions. Interpolation or shape functions. And you will get, so when you're putting the values of a0 and a1, a0, a1, a2, a3 in this equation, so that's equation number 8. So if you put the values of a0, a1, a2, a3 in equation number 8 and collect the coefficients of v1 theta 1, v2 theta 2, you will get these h1, h2, h3. So you will see that here, so where h1 will be equal to, the first shape function will be 1 minus 3x square upon l square plus 2x cube by l cube, and h2 would be equal to x minus 2x square upon l plus x cube by l square, and h3 will come out as 3x square upon l square minus 2x cube by l cube, and h4 will be, so these are the shape functions, no, x square by l plus x cube by l square. So these are the Hermite interpolation functions. So ultimately, you can say that v is equal to h into de, and where h is the, you already know the notation. So where H is nothing but consisting of these four Hermite interpolation functions, H1, H2, H3 and H4, and DE is nothing but V1E, theta 1E, V2E, theta 2E. So these are the degrees of freedom. Now before I actually go further, I want to discuss the properties of these Hermite interpolation functions. So earlier, no, for the two noded Truss element, we had two shape functions n1 and n2. N1 was 1 minus x by L and n2 was x by L. But now we have, the two noded Euler-Bernoulli beam element, but there are now 4 degrees of freedom for the element. And degrees of freedom are the transverse displacement V and its derivative dV by dx. So now this is the kind of shape functions you get. And now if we talk of properties of Hermite shape functions, properties means we are just talking about their values at node points. So let me say the node. So node number 1 is at local x equal to 0, node number 2 is at local x equal to L. So these are the node numbers, and the shape functions, let's look at the values h1, h2, h3, h4. And because the slope is also involved, so let us also look at the derivatives of these. So dh1 by dx, dh2 by dx, dh3 by dx, and dh4 by dx. So if you look at all these, so if you now put x equal to 0, the shape functions are already defined. No, these are h1, h2, h3 and h4 are there. So if you put capital X equal to 0, you will find that h1 would be unity and all the other h2, h3, h4, all of them will be 0. And when you take their derivatives and put capital X equal to 0, you will find this will be 0, dh2 by dx would be unity, and these two derivatives would be 0. Now in the shape functions, if you put capital X is equal to L, you will find that h1 would be 0, h2 would be 0, h3 would be unity, and h4 would be 0. In the derivatives, if you see, first you differentiate each h1, h2, h3 with respect to capital X, and then put x is equal to L, you will find this would be 0, this would be 0, this would be 0, and this would be unity. So you see h1 and h3 are, h1 is unity at node 1 and h3 is unity at node 2. dh2 by dx is unity at node 1, dh4 by dx is unity at node number 2. So this is one thing you would notice. Why it is so? Because no, the when we have v equal to h into d, and if we put x is equal to 0, so that must give us v1. So then h1 should be unity, rest of them should be actually 0. Similarly, when we put capital X is equal to small l in this approximation, so we should get v equal to v2e, and therefore v2e comes with the shape function h3, so that should be unity, and other shape functions should be 0. Similarly, when we take the derivative of this dv by dx, so dv by dx must be theta 1 e at x is equal to 0. So, and that is going with h2, so this should be unity, and rest others derivatives should be 0, and similarly for this. So you would see here that basically if you look at the shape functions, so h1 is say a shape function corresponding to v1e degree of freedom. If you look at h1, this is a shape function corresponding to v1e degree of freedom, DOF I am degree of freedom. And similarly, if you look at h3 is corresponding to v2e DOF. If you look at h2, h2 is corresponding to dv by dx at node 1 for the element which we are denoting by theta 1e DOF. And if you look at h4 is corresponding to dv by dx at 2 for the element which we are denoting by theta 2e DOF. So these are the various corresponding shape functions. So h1 is corresponding to v1, h2 is corresponding to v2, h3 is corresponding to v2, h2 is corresponding to theta 1, and h4 is corresponding to theta 2. So that is why the derivatives, the shape functions are their derivatives either 0 or unity at node 1 and 2, as discussed above. So now next thing, of course, what we do is we substitute this approximate solution given by v equal to h into d, this expression in the integral functional, and then we take the variation of the integral function and equate it to 0 for any arbitrary variation in the vector of elemental degrees of freedom, and we get the element level governing equation. So those steps are exactly same what we discussed for the the two noded or three noded truss element. So the steps are exactly same, so you should be able to derive. Only thing is you need now d2v by dx square. So d2v by dx square will be equal to the dh1 by dx square, dh2 by dx square, dh3 by dx square, no, d2h1 by dx square, d2h2 by dx square, d2h3 by dx square, d2h4 by dx square, and into vector of elemental degrees of freedom, that is v1e, theta 1e, v2e, and theta 2e. So we call this as b, and this as your de. So this is b, strain displacement matrix, and this is the vector of elemental degrees of freedom. So before you can, so I'll just I think I want to just conclude over here. So before you can substitute this in the integral functional, so you will rewrite that I, so that the matrix and vector multiplications are consistent. So you will write this as half integral 0 to L, and then we have ei and d2v by dx square transpose, the way we did earlier, d2v by dx square dx, minus the second term we write v transpose q dx, and the third term we write in terms of vector of elemental degrees of freedom v1 theta 1e, v2e, theta 2e transpose, and then we have now the shear force, bending moment at node 1, shear force and bending moment at node 2. So this is the your integral functional. So if you substitute over here, you will see I equal to half integral 0 to L, and you have ei, and this side you will get, I know the d2v by dx square transpose would be d transpose into b transpose, and then d2v by dx square is b into de dx, minus this term would be integral 0 to L v transpose would become d transpose into h transpose into q dx, and then minus that is de transpose and into the internal force vector. So now in this term, d transpose can be taken on the left hand side out of the integral, this d can be taken right side out of the integral, this d transpose can be taken on the left side out of the integral, and then delta I equal to 0 will give you the element level governing equation. So I think I want to stop here. We will continue in the next class, but you try to, from this point onward, try to develop the element level governing equations. So I want to stop here, and if you have any questions and doubts, now you can ask. Yeah, so I think no, there was a question about can I explain the first two terms of the total potential energy functional. So we have already discussed. No, if you remember, if you go through the earlier notes when I had discussed the big Forman and the integral functional, I had given a detailed discussion on of what are these terms in the total potential energy functional. So this first term is the strain energy. No, this whole term is the strain energy, and this is the potential energy of the distributed force Q. So you need to look at the earlier lecture notes or the video. We have already discussed in detail how we arrive at this. The total potential energy functional for Euler-Bernoulli beam element. So the first term is strain energy, second term is the potential of externally applied distributed force Q, and these are the potential energies of internal forces, shear force S1, bending moment M1 at left side, and shear force S2 and bending moment M2 at the right side. So these are the potential energy terms. Yeah, so are there any other questions? Anybody has any other question? Okay, so if there are no questions, I am stopping here. Thank you all for your attention. And please go through all the steps and make sure that you understand all the things. So, the understanding the concepts is important. And yeah, so I think I will, yeah, so I stop here. Thank you all for your attention. I will mention the regarding the assignment submission, I will mention in the next class. There are some issues. I think you people have to be more honest.